NENOMATICA, where mathematics meets YouTube excellence. Welcome to today's math lesson on the properties of nth roots. We'll be exploring some important rules to remember when working with roots. Let's begin with our first property. We agree that if n equals 2, we write the square root value. That is, the nth root of x when n equals 2 equals the square root of x. Now, let's look at some important facts to remember. First, the nth root of 0 equals 0. Second, the nth root of 1 equals 1. For any value of n, that is a natural number. Third, the nth root of -1 equals -1. When n equals 2k plus 1, meaning n is an odd number. Let's move to our second property. Although the following equality is true, 3 squared equals -3 squared equals 9, we agree to write the square root of 9 equals 3. This is because the square root of a positive number is always positive. We never write the square root of 9 equals -3. The result of an even root of a non-negative number is always non-negative. To solve this problem, we use the concept of absolute value as follows. The square root of a squared equals the absolute value of a. Let's look at some examples of this concept in action. First, the square root of -6 squared equals the absolute value of -6, which equals the absolute value of 6, which equals 6. Next, the square root of b to the 4th power times c to the 4th power equals the square root of b squared times c squared, which equals the absolute value of b squared times c squared, which equals b squared times c squared. Finally, the square root of a to the 8th power equals the square root of a to the 4th power squared, which equals the absolute value of a to the 4th power, which equals a to the 4th power. Welcome to this math tutorial. Today, we're going to explore some fundamental properties relating square roots and absolute values. Specifically, we'll examine the identity that the square root of a squared number equals the absolute value of that number. Let's start with our first example. We want to verify that the square root of -3 squared equals the absolute value of -3. To solve this, we'll use a fundamental rule in mathematics. The rule states that the square root of a squared term equals the absolute value of that term. This is because the square of any number is always non-negative, and the principal square root always returns the non-negative value. Now, let's solve our example step by step. First, we'll evaluate what's inside the square root, which is -3 squared. When we square -3, we get +9. Now that we have 9 inside the square root, we'll take the square root of 9, which is 3. Remember, the square root function always returns the non-negative root by convention. Finally, we need to determine the absolute value of -3. The absolute value gives us the distance from 0, which for -3 is 3. Therefore, we verified that the square root of -3 squared equals the absolute value of -3. Both evaluate to 3. Let's look at another example. This time, we want to verify that the square root of 5 squared equals the absolute value of 5. We'll apply the same rule as before. Let's solve this step by step. First, we'll evaluate 5 squared, which is 25. Next, we'll take the square root of 25, which is 5. Finally, we'll find the absolute value of 5. Since 5 is already positive, its absolute value is also 5. Therefore, we verified that the square root of 5 squared equals the absolute value of 5. Both are equal to 5. Let's examine one more example, which is slightly more complex. Here, we want to verify that the square root of 4 squared equals the square root of -4 squared, which equals the absolute value of -4, which equals the absolute value of 4. We'll apply our rule again. Step 1. Let's evaluate 4 squared and -4 squared. 4 squared is 16, and -4 squared is also 16. Step 2. We'll take the square root of 16 in both cases, which gives us 4. Step 3. We need to determine the absolute values of 4 and -4. The absolute value of 4 is 4, and the absolute value of -4 is also 4. Therefore, we've verified all the equalities in our statement. They all evaluate to 4. Welcome to our math lesson on odd-indexed roots. Today we're going to explore an important concept in radical expressions, specifically how odd-indexed radicals behave with negative numbers. Let's begin by understanding the key principle. If n is odd, Then in addition to positive numbers, negative numbers can also have defined odd-indexed radicals. For example, the cube root of -8 equals -2. Let me show you why this works. Let's verify this result. We know that -2 cubed equals -8. That is, -2 times -2 times -2 equals -8. This confirms our solution. Now, let's practice with a few exercises. Our first exercise is to find the value of the cube root of -125. Let's solve this step by step. First, we rewrite this as the cube root of -1 times 125 cubed. Next, we can write this as the cube root of -1 times the cube root of the quantity -5 cubed. We can expand the inner expression as -5 times -5 times -5. This simplifies to -125. So, our answer is -5. Let's try another example. Find the value of the cube root of -a cubed. Let's solve this step by step. First, we rewrite this as the cube root of -1 times a cubed. The cube root of a cubed is simply a, so our answer is -a. Let's try one more example. Find the value of the cube root of b to the 6th power. Let's solve this step by step. We can rewrite this as the cube root of b cubed times b cubed. Using the property of radicals, this is equal to the cube root of b cubed times the cube root of b cubed. And we know that the cube root of b cubed equals b. So, our answer is b squared. Let's tackle one last example. Find the value of the cube root of x to the 4th power times x to the 5th power. Let's solve this step by step. First, we simplify inside the radical. X to the 4th power times x to the 5th power equals x to the 9th power. Next, we can rewrite this as the cube root of x cubed to the 3rd power. Using the power property of radicals, this equals the cube root of x cubed. Let's summarize what we've learned today about odd-indexed radicals. 4 odd indices, like cube roots, both positive and negative numbers, can have real roots. The cube root of a negative number equals the negative of the cube root of the positive number. We've solved examples with numerical values and variables, applied important radical properties, including the product and power properties. Welcome to our lesson on radical expressions. Today we'll be learning about surd expressions and when radicals become invalid in the real number system. Let's start by understanding what a surd expression is. A surd is a radical expression that cannot be simplified to a rational number. For instance, the square root of 2, the cube root of 9, the 5th root of 34, the square root of x squared plus 1, and the 7th root of 275 are all examples of surds. Now, let's discuss when radical expressions become invalid in the real number system. If the index of a radical is even and the expression under the radical is negative, then the radical expression is meaningless or invalid in the real number system. For example, the square root of -4, the square root of -81, the 20th root of -5 to the power of 20, the 4th root of -2 to the power of 4k, and the 4th root of -x squared plus 1 to the power of 4, where x is a real number, are all invalid in the real number system. We need to find the cube root of -8. To solve this problem, we need to find a number that, when cubed, equals -8. Let's think about this. When we cube a negative number, we get a negative result. So we're looking for a negative number whose cube is -8. Let's try -2. -2 cubed is -2 times -2 times -2, which equals -8. So we can write the cube root of -8 equals -2. And we can verify this by checking that -2 cubed equals -8. Let's move to our second example. Here we need to find the 5th root of 32. Using the same approach, we need to find a number that, when raised to the 5th power, equals 32. Let's try 2. 2 to the 5th power is 2 times 2 times 2 times 2 times 2, which equals 32. So the 5th root of 32 equals 2. And we can verify this by checking that 2 to the 5th power equals 32. For our third example, let's find the 6th root of 64. Again, we need to find a number that, when raised to the 6th power, equals 64. Let's try 2. 2 to the 6th power is 2 to the power of 6, which equals 64. So, the 6th root of 64 equals 2. We can verify that 2 to the 6th power equals 64. Now, let's solve a more complex problem. Find the value of the fifth root of negative 1 over 32. To solve this, we'll need to find a number that, when raised to the fifth power, gives us negative 1 over 32. The key insight here is that this can be rewritten as the fifth root of negative 1/2 to the fifth power. Let's see how this looks. Now we can apply the definition of the nth root. The fifth root of negative 1/2 to the fifth power is negative 1/2. So our answer is negative 1/2. Let's move on to another example from our problem set. Calculate the square root of negative 3 times negative 3 cubed minus the square root of 81. First, let's simplify the expression inside the first square root. We have negative 3 times negative 3 cubed. Negative 3 cubed is negative 27. So we have negative 3 times negative 27, which equals positive 81. Now, we need to find the square root of 81. The square root of 81 is 9. So we have 9 minus 9, which equals 0. Therefore, our final answer is 0. For our final example, let's evaluate 2 plus the cube root of negative 8. We already determined in our first example that the cube root of negative 8 equals negative 2. So we have 2 plus negative 2, which equals 0. Let's summarize what we've learned about solving nth root expressions. The key definition is that the nth root of a number equals a value be if, and only if be raised to the power of n equals a. For even roots like square roots, we need to remember that the input must be non-negative. For odd roots, we can have negative inputs, and the result will have the same sign as the input. These principles allow us to solve a variety of root expressions, from basic ones like the cube root of negative 8 to more complex ones involving fractions and multiple terms. We need to evaluate 5 times the square root of 9 plus 2 times the square root of negative 4 squared minus 3 times the square root of negative 3 squared plus 2 times the square root of 9 minus the square root of 64. Let's apply the rule that says the square root of a perfect square equals the absolute value of the base. So we have 5 times the square root of 3 squared plus 2 times the square root of negative 4 squared minus 3 times the square root of negative 3 squared plus 2 times the square root of 3 squared minus the square root of 8 squared. Now we apply the rule that the square root of a square equals the absolute value. So 5 times 3 plus 2 times 4 minus 3 times 3 plus 2 times 3 minus 8. Let's simplify this step by step. 5 times 3 is 15. 2 times 4 is 8. 3 times 3 is 9. 2 times 3 is 6. So we have 15 plus 8 minus 9 plus 6 minus 8. Finally, let's add all these terms together. 15 plus 8 is 23. 23 minus 9 is 14. 14 plus 6 is 20. 20 minus 8 is 12. Therefore, our final answer is 12. Let's move on to our second example. We need to evaluate 7 times the square root of 4/9 minus the square root of negative 2/3 squared plus 10/3 minus 11 times the square root of 4/9. For our second step, we need to rewrite the square roots. The square root of 4/9 is 2/3, and the square root of negative 2/3 squared also equals 2/3, since we take the absolute value. So we have 7 times 2/3 minus 2/3 plus 10/3 minus 11 times 2/3. Let's multiply the fractions. 7 times 2/3 is 14/3. 11 times 2/3 is 22/3. So we have 14/3 minus 2/3 plus 10/3 minus 22/3. Now, let's combine these fractions. We have 14 minus 2 plus 10 minus 22, all over 3. That's 22 minus 22, which is 0 all over 3. So our final answer is 0 over 3, which simplifies to 0. We need to solve the expression 2 times the square root of negative 0.1 squared minus 5 times the square root of 1 over 100 plus 4 times the square root of 0.25 minus 7 times the square root of 0.09. Let's start by using the principal root property. For any real number, a, the square root of a squared equals the absolute value of a. In our first step, we'll rewrite the decimal values in our expression as fractions to make them easier to work with. Negative 0.1 can be written as negative 1/10. 1 over 100 is already in fraction form. 0.25 equals 25 over 100, and 0.09 equals 9 over 100. Quick challenge. Can you see why we wrote negative 0.1 as negative 1/10? It's because 0.1 is equal to 1/10, so negative 0.1 equals negative 1/10. Moving on to step 2, we'll use the tip that the square root of a squared over b squared equals the absolute value of a over the absolute value of b. Now we can simplify each radical term. The square root of negative 1/10 squared equals 1/10, since the square root of a squared gives us the absolute value. Similarly, the square root of 1/10 squared is also 1/10. The square root of 25 over 100 is 5/10, and the square root of 9 over 100 is 3/10. Pause for a moment to recall that radicals return non-negative values. That's why when we take the square root of negative 1/10 squared, we get positive 1/10. Now for step 3, we multiply each coefficient by its corresponding fraction. 2 times 1/10 is 2/10. 5 times 1/10 is 5/10. 4 times 5/10 is 20/10. And 7 times 3/10 is 21/10. For step 4, we combine all these fractions over their common denominator, which is 10. So we have 2 minus 5 plus 20 minus 21 all over 10. In step 5, we compute the numerator. 2 minus 5 is negative 3. Negative 3 plus 20 is 17. And 17 minus 21 is negative 4. So our expression is negative 4 over 10. Finally, in step 6, we reduce this fraction to its simplest form. Negative 4 over 10 simplifies to negative 2 over 5 by dividing both numerator and denominator by 2. So our final answer is negative 2/5. We have a complex expression. 3 times the square root of 9 over 4 minus the square root of the quantity negative 3 over 2 squared minus 2 times the square root of 9 over 4 plus the square root of 9 over 2 minus 3 over the square root of 4. Let's begin by simplifying each term. First, let's simplify the square root of 9 over 4 to 3 over 2. We'll do this step by step. Now, let's continue simplifying. We know that the square root of a squared value equals the absolute value of that number. So, the square root of 3 over 2 squared is 3 over 2. And the square root of negative 3 over 2 squared is also 3 over 2. Also, let's simplify the square root of 9 to 3, and the square root of 4 to 2. Let's calculate each term. 3 times 3 over 2 equals 9 over 2, or 4.5. 3 over 2 remains the same. 2 times 3 over 2 equals 3. 3 over 2 remains the same. And 3 over 2 remains the same. Now we can combine like terms. 9 over 2 minus 3 over 2 minus 3 plus 3 over 2 minus 3 over 2. First, let's calculate 9 over 2 minus 3 over 2, which equals 6 over 2, or 3. So we have 3 minus 3, which is 0. And then 3 over 2 minus 3 over 2, which is also 0. So our final answer is 0. Now, let's move on to our second example. Here we have another complex expression. 7 times the square root of negative 4 squared minus 5 times the square root of negative 2 to the power of 4 plus the square root of negative 4 to the power of 4 minus the square root of negative 2 squared. Let's start by evaluating the powers. Negative 4 squared equals 16, and negative 2 to the power of 4 equals 16 as well. Also, negative 4 to the power of 4 equals 256, and negative 2 squared equals 4. Now, we can evaluate the square roots. The square root of 16 is 4, the square root of 256 is 16, and the square root of 4 is 2. Let's calculate. 7 times 4 equals 28, and 5 times 4 equals 20. So, we have 28 minus 20 plus 16 minus 2. Now we can add and subtract. 28 minus 20 equals 8, plus 16 equals 24, minus 2 equals 22. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.